Example 5. In a standard vapor compression refrigeration cycle, operating between an evaporator temperature of -10 degrees Celsius and a condenser temperature of 40 degrees Celsius, the enthalpy of the refrigerant, Freon 12, at the end of compression is 220 kilojoules per kilogram. Show the cycle diagram on TS plane. Calculate 1. The COP of the cycle. 2. The refrigerating capacity and the compressor power, assuming a refrigerant flow rate of 1 kg per minute. You may use the extract of Freon 12 property table given below. Before start the question, let's discuss about vapor compression refrigeration system. The main difference between the air compression system and vapor compression system is, in the vapor compression system the refrigerant is converts into liquid and vapor during the refrigeration process. Therefore we have to deal with both liquid and vapor states of the refrigerant. Vapor compression refrigeration system consists of 4 components. First one is a evaporator. In the evaporator, liquid refrigerant evaporate by absorbing heat from the object to be cooled. Second one is a compressor, which compress the evaporated refrigerant and increase the temperature and pressure. Third one is condenser. In the condenser the vaporized refrigerant condense by removing heat. Fourth one is the expander, which expand the refrigerant and decrease the pressure and temperature. There are mainly 3 types of vapor compression cycles. First case is the vapor superheated after the compression. The corresponding temperature entropy diagram and pressure enthalpy diagram show below. Note that here the point 3 is in the superheated region. This is also called standard vapor compression refrigeration cycle. Here we have to draw the saturation curve in the TS and pH diagram. The saturation curve separate the superheated vapor region, subcooled liquid region and liquid vapor two-phase region. Second case is, the vapor is dry and saturated at the end of the compression. The corresponding temperature entropy diagram and pressure enthalpy diagram show below. Note that here the point 3 is in the vapor saturated line. Third case is, the vapor is wet after the compression. The corresponding temperature entropy diagram and pressure enthalpy diagram show below. Note that here the point 3 is in the two-phase region. Here, at the end of the compression the liquid is not completely vaporized. There is liquid phase refrigerant after the compression. Also you should know about the refrigerant properties table. A part of the ammonia refrigerant, R717, is shown below. Here if you know the saturated temperature or pressure values you can find the corresponding enthalpy, entropy, liquid density values of the refrigerant. Let's move to the question. Since this is a standard vapor compression refrigeration system, the temperature entropy diagram is as follows. Here we can mark the heat absorption QC, in 1 to 2 process. Heat released QH, in 3 to 4 process. And work done by the compressor W, in the 2 to 3 process. Here 1 to 2 process is isothermal and isobaric. 2 to 3 process is isentropic. 3 to 4 process is isobaric. The corresponding pressure, enthalpy diagram is as follows. Here we have given, temperature of the evaporator Tc equals -10 Celsius. Temperature of the condenser Th equals 40 Celsius. Enthalpy of the refrigerant at the end of the compression H3 equals 220 kJ per kilogram. Refrigerant flow rate equals 1 kg per minute. Part 1. COP equals QC divided by W, which is equals heat absorbed by the refrigerant divided by work done by the compressor. Which is equals H2 minus H1 divided by H3 minus H2. Here we have given the H3 equals 220 kilojoules per kilogram. By the refrigerant table, H2 equals enthalpy at the end of the evaporation equals 183.1 kilojoules per kilogram. H1 equals H4 equals enthalpy at the end of the condensation equals 74.53 kilojoules per kilogram. Note that, here Hg2 means enthalpy of the saturated gas at point 2. HF4 means enthalpy of the saturated fluid at point 4. Therefore, substituting the enthalpy values, we get COP equals 2.94. Part 2. we know COP equals refrigeration effect divided by power of the compressor, here refrigeration effect equals heat absorption rate of the refrigerant, which is equals to H2 minus H1 multiply by refrigerant flow rate. By substituting the values we get, RE equals 108.57 kilojoules per minute. Therefore the power of the compressor equals RE divided by COP, which gives 36.9286 kilojoules per minute. Which is equals to 0.615 kilowatts.